How do I actually know that it's recording? Or is it not making that noise? Okay, so we're going to talk about the next part here, which is dealing with histograms. Okay, so histograms are something that you might have seen from GCSE from before, and they are different to bar charts. The main thing that actually makes them different is what we have here on the y-axis. So here's an example of a histogram, and it has frequency density against age. It's quite common that we have some kind of continuous data on our x-axis, and we also notice that these bars are next to each other and there are no gaps, which fits with the idea that it's continuous data as well. And if we look at some quick questions to start off with, how many visitors were under 10? So it's very tempting to look at this and say that this is 30, the frequency is 30. But as the hint tells us, this is not the case, because the way that histograms work is they plot frequency density. Frequency density, there's a formula for this one. It's equal to the frequency divided by the class meaning like a group, okay, the class width. So, for example, on this first box here, the frequency on the top is 30, and the class width means the gap between 0 and 10. So, the frequency density should be here. So if I fill this in, I could say 30, which is the frequency density here, is the frequency divided by 10. And I could rearrange and answer 300. More simply, you might actually say that the area of the rectangle represents the frequency. This is fine as long as there's no scale factor, which is something that's new to the A-level spec. So for example, assuming there's no scale factor again, we could say that this goes up to 60. It's 10 wide, so this represents 600 people, and so on. Okay, so we've talked already, histograms are for, let's just reveal this one here, are for continuous data, and some of the characteristics are that frequency density is on the left-hand side, the y-axis, there's no gaps, and these do not necessarily have to be even class widths. As you see here, this seems to be going from 1 to 1.3, whereas the other ones seem narrower. Compare it to a bar chart, this is for discrete data, and the actual height tells you the frequency, which is obviously more simplistic. A common question might be to take the class, which is weight here, okay, look at the width, look at the frequency, and to work out the density, and you might do this to plot it. So for example, we see that we have frequency divided by class width gives frequency density, this is 4, and you could plot this on a diagram. The same again, the class width is 5, frequency is 6, okay, and we could divide frequency by class width. As you just saw as well, we are expected to sort of go backwards, so a multiplication here gives us 52 and gives us 10. And you need to be able to move confidently between the table and bars. So you need to be able to read off information here and go backwards, or calculate information and then plot this. Okay, and some answers are given for you there on the screen. Frequency, as we said, can often be found by calculating the area of bars, as long as their scale factor is 1. However, this is not always the case. For A-level, you might find that you need to scale the area. And the basic technique for this is you're going to either take information from frequency from the question, or you're going to calculate from the area of bars on a diagram, and then you are going to decide how much one would have to be scaled up. Scaled up, multiplied by some number. So for example, there were 60 runners in a 100-meter race. The following histogram represents their times. So we might notice, first of all, that this category here, from 9 to 12 seconds, this is a width of 3, and the frequency density is 5. And if you remember, we can multiply these to get our frequency. That's what we said from before. If we did that, the frequency that we would get would be 5 times 3. It would be 15. If we did the same thing again, what would we get for this one here? So 1.5 times the width would be 6. So 6 times 1.5, we would get a frequency of 9. However, if these are all the bars that we have, we notice that our total frequency from the diagram seems to be 24, but from the information worded seems to be 60. So what's going on here? Well, the frequency from the diagram, 24, must be multiplied by some number. It must be scaled up to create this 60. We might do this if the frequency is very, very high, or maybe if we don't have enough space on the diagram. We might use some scale factor here. And our inverse operations would tell us that we needed to do a division here to find out what the scale was. So as we can see, the scale is 2.5. And then we can answer a question perhaps in the normal way. So determine the number of runners with times above 14. Well, above 14, if I assume that the runners are equally distributed here, I have a fraction of this whole bar. So from 14 to 18 is 2/3 of this bar. This total bar is 9. So 2/3 will give me 6. And then I need to apply the scale factor. And this will tell me the actual frequency, which is 15. So what you're doing is you're kind of connecting information from the question with what you see from the diagram to see if anything needs to be scaled up. Okay, here is another example of a question that applies the same kind of idea. And there's actually a number of techniques that you can use here for when frequency density is not given to you on the left-hand side. One suggestion is you can just apply your own scale. So if frequency density is not given to you, you might notice these large squares here, and you can just assign them a 1, a 2, and a 3, and then complete this question as we did the one before. You have 450. You would use these numbers on the diagram to express these areas, and this would allow you to solve the question. Alternatively, you can create your own system as long as you're consistent with this. So for example, you may wish to look at complete squares. There's a complete square here and a complete square here. So I could call this all together 1.5 large squares. There's a large square here, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 12, and so on. And you can repeat this. You will get a different scale, you'll get different working out, but this approach will also enable you to solve the question. Okay, I'm just going to reveal here. What they've done is they've made up their own scale with each sort of smaller square, but not the smallest, as 1. And if you do that, you will get this scale. However, you will get a completely different scale if you used my numbers in red, or if you counted large squares by shading them in and counting squares. You'll get different answers. The key is you need to be consistent with this because we're interested in their proportions to each other. This is why this works. Okay, and just on this question, just make sure that we're not sort of answering anything completely different. So once you've established scale, for example, don't forget that you can be asked about things from the previous chapter, such as estimating the mean. Estimating the mean, you want to use midpoints. Okay, you want to be using midpoints here and frequencies, which you should have found out in the A part of the question. Again, revealing these for you, but you should check you can get these yourself. Okay, and finally, we should talk about how we handle any gaps that we might be given as well. So, if we have weight to the nearest kilogram, remember we had this in chapter 2. So weight to the nearest kilogram, well, what is to the nearest one? Actually, it's 0.5, and this could go all the way up to 2.5. 3 actually starts at 2.5 and goes up to 6.5, and so on. So just like when we had linear interpolation, it's important to make sure that the data connects, because histograms, for continuous data, we shouldn't have gaps between them. Okay, and you have an associated test your understanding question on the board to have a quick go at. So pause here to have a go. Okay, and this question here, if you've had a go at it, you'll find it's actually quite a challenging question. It talks about to the nearest minute on here, which will affect boundaries and calculations. So this one here perhaps is drawn a little bit small to help you out, but you may have been able to do this one. And we're going to leave it there until the last lesson on histograms. So key ideas really to take from this, I would say, are scaling, the idea that we can scale, so compare frequencies together, total frequencies from diagrams and from questions, and also learning how to handle situations where frequency density isn't given to you. You can simply assign your own numbers, and this will work as long as you are consistent.